Okay, record is on.
Hello, good afternoon. Welcome to a new CRID Webinar Series. Today we have Khaled Elashry from Forces and Partners all the way from London joining us. Just a little bit of introduction about Khaled, whose interests combine architecture and computer science, and he's currently holding the position of Associate Partner at the Applied R&D Group at Forces and Partners, in addition to teaching at Bartlett School of Architecture. His work bridges the gap between practice and research with expertise in optimization, fabrication, robotics, and XR. This is a little bit of introduction about Khaled, and for any questions, please send them to me privately or just type in your question in the Q&A session, and I will be directing the questions at the end to Khaled for the Q&A session. That's all from my side now, Khaled. It says you, so please just feel free to share the screen and go ahead.
Yeah, okay. Thank you guys for having me. I'll just go through sharing the screen. Starting the presentation. So thank you everyone for having me. As Mohammed said, I'm working for the Forces and Partners office in London, and I'm part of the Applied Research and Development team. And a lot of the work that I'm going to show you today is actually the work that we do in the group. So give a small introduction to the group first. So we are a multidisciplinary team. We have architects, software developers, mathematicians, and artists. And basically, we aim to get the latest technologies in the hand of the architects, of our architects and designers. We cover a lot of topics, from complex geometry to performance-driven design to machine learning. So we have done many projects and initiatives in each of these topics. And you name it, we probably have done something related to it. In terms of project, we work on a wide range of scales, from furnitures all the way to cities. And projects around the globe as well, but all of it started for the team was a Gherkin. The Gherkin, which now is probably around like 20 years ago. It was a pioneer project at this time. For example, it was one of the first projects that used the CFD to simulate wind around the building, for example. But what not a lot of people know is that the design of the exterior shell was actually done in Excel. And Excel is a very powerful tool for anyone who know how to use it, because you can basically build programs inside it. And this is way before Grasshopper, way before any parametric design model. And what you can see here is actually the inputs to all the VB scripts that can create the shell, and then basically went and created all the locations of the nodes in a MicroStation using this Excel program. So moving to a kind of more current projects, I was very fortunate to work on the Mobility Pavilion in Dubai Expo, and it was a process for multiple years. And basically, when we won the competition in 2016, we started working on how we can produce a facade package in order to get it in time built, because as you know, expos have a very limited time in order to finish the project. I mean, we had like one extra year, obviously it was COVID for this project, but when we started, we had a very, very short period in order to finish all our design. In order to make sure that our designs are going to be built in time and built correctly, we started from the base geometry of the building itself. So we wanted to start from very clean and very easy geometry to control. And what we had was kind of like the sheared cones that then are connected with filleted surfaces in between. And from these surfaces, we started building a parametric model that didn't allow us to produce all the fins all the louvers that are around the building facade. And what we wanted to do is we wanted to have a lot of control over the quality of the geometry, which is something very important. For example, on the left, when you use just a sweep from Rhino, you start getting this bulges in the geometry, which actually means the geometry is not very clean and straight. And instead, we wanted to have like full control of how the geometry is generated, which meant we started producing these sections for all the louvers around the building every 10 centimeter. And this allowed us to make sure that the geometry have the tangency and can easily control all the straight line and arcs in it in every part of the project. So you can easily cut through it and you can get a clean section. We also wanted to make sure that there is a nice transition in all the geometry. So we used a sine curve, as you know from any lessons in math. If you draw a sine curve, you get like tangency on both ends of it. And then when you apply this to the transition of the geometry, it means that we're getting something that's very smooth and very nicely integrated as well. So we're very happy with what was the geometry that we produced for the project. During the project as well, we're working on some ways that we can move the geometry where we're modeling, which is Rhino, to where all our documents want to be, which is Revit. And we built a pipeline so basically you can easily model in Rhino, and you get all the geometry packages as well in Revit, which means that every time the design team is changing something, we can get all the geometry sent in very quickly, and all the kind of documents generated out. So with our work didn't stop there because it's continued during the construction as well. So we're doing work with 3D scanning, making sure that the geometry that's on site is matching whatever we're producing. And then this continued, for example, through the years as well. For example, all here what you see is one of the beams that were on site. And after the beam was finished, we found like some discrepancies between where the beam is and where our model is. So what we do is we're actually generating the facade geometry while the site is also building the building itself. And this means that we can adapt to any problems that we have on site, and then we can update our model, regenerate the facade, and then the factory can go and start manufacturing all these things. And the results were quite nice. I got to visit as well during Expo, and I was very happy to see it built. So we do a lot of projects with geometry, but we also do a lot of other interesting stuff as well. So this is one of the projects that we worked on before, which is a UE Pavilion for Milan Expo. And our job was actually trying to generate this kind of sand dune patterns that's on the inside and on the outside of the facade. And in order to do so, we use something called the reaction diffusion. And then here you can see how we generate this kind of patterns organically, but at the same time, because we generate it using the computer, we can control the edge boundary conditions of all the patterns, which means that we can actually easily move them around and still tie nicely. And this was quite important because, again, it was like a very short period and everything needs to be manufactured in time. And we were actually manufacturing the panels in China, where they were using the molds in order to create these GRC panels. And this molds needs to be used, I think, up to 7 times in order to be economically viable, in order to finish the project in time. So in order for us to be able to use it 7 times, what we've done is done something I call an optimization. And what the optimization is basically you go and ask the computer to generate thousands and thousands of options. Every time it generates options, it starts to find out which options perform better, and then it tries to combine these better performing options until you get to like and options is much better from where you started with. So in here, what we wanted to do is wanted to make sure that the repeated patterns are not that close to each other in the building. So basically, when you see all this pattern on the outside, you don't see any of the repetition. So we built a parametric model, and we managed to reduce the molds quite a bit, and also make sure that you won't see any of this repetition outside. And the results, the finished result was really impressive. And what was the great thing about this project as well is usually it was exposed. All these building gets torn in the end of them, which is very wasteful. But for this project especially, it got all packed again and sent to the UAE in order to be the UAE Space Agency center, which means have like a new life as well after Expo is finished. So I talked to you a little bit about optimization. So we do this a lot on buildings in the office. So what we're trying to do is trying to get the best options, best performing option out of our designs, right? And we do that. We also try to do a lot of performance metrics. For example, here we're looking at views. So we want to make sure that each of these apartments in this project in San Francisco have a view to one of the targets, which is like the Golden Gate or the view as the water views and so on. And basically, you can combine two. We can start trying to figure out building layouts that maximizes views to the outside. You can do that on 2D. You can do that on 3D as well. So you can see this building starts very randomly, and bit by bit starts to figure out where it's kind of like its best form. And then at this time, this is where we go in and start checking these forms. Options are working to the best performance. So doing it on building is very trivial. A lot of people do it, and you can do it in your machine if you have running the software. But we wanted to take this even further. So this is a project that we have done in Guangming in China. It was a competition that we won recently. And basically, it was a massive master plan for a city surrounding this kind of hub, transportation hub in the middle. As you see, when we started, wanted to try to run this optimization, but on the scale of a city. And we managed to do it in this project. So in order to do it, we start by generating like roads, and then we start placing buildings from these roads. And then we have a set of analysis that we define if each of the options is performing well or not. And then basically afterwards, we have this design explorer that we give to the designers, and they can start checking which option is performing best in one of the criterias. And the results were really good. We won the competition. It became like one of the big projects that we have in the office. So how are we doing it? Actually, as I told you, it's easy to do it on one machine for one building. But when you start looking at the city scale, it becomes much harder. So what we do is similar to what people use in the industry, in the like 3D rendering industry. So we distribute everything to multiple machines. So we actually send our grasshopper definition to all the machines that are ideal in the office, and we do run the optimization all of them at the same time, which means that something that will take weeks in order to produce a result can take like just a day or two. And we use it a lot. We combine this kind of like fast analysis that we build and the fast optimization in order to get like these results out very quickly. We have done that for another competition as well that we have done, basically called Vanderbilt University in Nashville. Again, we start by building like a parametric model that can kind of cover a lot of solutions in terms of how this building is working. And then we go and basically ask the computer to run as much options as possible and see what kind of results we're getting in the end. So yeah, so sorry, we're missing one. And we get again, lots of options in the end, and you can choose which option you want to use for the final design. Yeah. So I'm going to move to some other stuff that's a little more cool. Actually, I think we have a problem with the videos. Let me just restart quickly, and I'll start the presentation again. Okay, sorry. Okay, let's see. Just solve that. Technology never works when you need it to work. But yeah, here we go. I think this works now. Yeah. So in our team, what we do is we actually code a lot of design programs that we use. And this is one example that we've done now, I think 13, 14 years ago, that was looking at basically giving you a lot of information while you design. This information can be the performance of the buildings in terms of environmental data. It can be connectivity or how the building is moving in it. It can be stuff related to views. And we have been upgrading the software through the years. We also tried doing it on physical models. So this is an example of it that we're basically scanning this physical model. We're having a digital representation of the model while we're working on it. And then we can define if any of these models are performing well or not. So it kind of brings in the digital and physical together into one piece. This is kind of the latest version. One of the latest versions that we've done is called Sandbox. And it's basically Minecraft for architects, where you can go and build options very quickly. But while you're doing so, you're also getting feedback in terms of analysis and performance of your option. So you can see it here. We can run it in multiple interfaces from a PC to or an iPad that a partner can have, and you can be drawing on it while he's in a plane somewhere, or even in VR. You see here one example of the project. It's called this was called Sisto. It's a master plan that we have done in Milan. And you can see here you can easily quickly model your buildings. But what you can do as well, which we will see in a second, you can start by, for example, seeing how the shadow and so on is working, and you can run analysis on it. So, for example, this is analysis for the green. This is analysis for radiation. So, you're looking at where's the parts that have the most radiation on them. And then, for example, here we can remove one part of the building, and you would see how it affects the rest of the building in real time, which is it's very variable. We can also add some other metrics like well-being and some other sustainability metrics like you hear a lot about embodied and operational carbon whenever you go to the industry afterwards. So even these calculations you can have, so you can make like informed decisions early in the process rather than doing it later on. This is the latest iteration of our software. It's called Talia. And again, it revolves all around getting as much information as possible from a model. You can see here, you can run analysis, you can change between options, and you can actually check how each of these options is performing, which means you can choose any of them accordingly very quickly in the beginning of in the concept stage. Moving to another topic, which is like actually VR and AR. What you see actually is my apartment during the pandemic. So and these are my colleagues, Sharif and Zahao. And we had like basically having a virtual meeting, but it's as if it's all on the same space. And we look a lot into this kind of technologies and how people will basically design in the future and interact as well in virtual spaces. So as you see, like the design process changes and evolves as well greatly through the year. So this is a picture of our office when it was opened in the early 90s. And what you can see is you might see like a couple of computers, but actually most people have massive drawing boards and they're working manually. In the 2000s, you can see we have a lot of screens, but we have a lot of paper as well. In the 2010s, you can see that we have less paper, but more screens. And then in the 2020s, during COVID, we decided to actually go and build a virtual space that looked like the office. So people can go and do meetings in the space as if they're in the office itself. And afterwards, we had a tool called Cloudroom that's led by my colleagues David and Sahau. And basically what they're doing here, you can have reviews for different models, and people can be in different places. Someone can be working from home, someone can be working from the office, but they're all working at the same time. So what other things we can do with this kind of technology, right? In the office here, we do a lot of full-scale mockups. So what you see on the left of the image is actually a full-scale mockup of the entrance for the JP Morgan Tower in New York that we have done, that we're working on recently. And on the left is a VR version of the same entrance with the materials and the nice finishes and so on. And what we can do is we can combine both. So actually someone can walk into the space on the left, but see everything on the right. And this is quite important because when you do it, that means you have a sense of scale and a sense of space and surroundings, but have all the finishes and all the quality of the kind of high quality VR models that we have. So we combine those together. We can take this even further and try it on the outdoors. So for one of the projects that we have done, we actually took the whole process to the site itself. And basically you can be on site and you can feel all the surroundings, the noise, the temperature, the location itself. But you can be having a headset that can actually see the building on location. And this can be a very powerful tool, especially when you're working with councils and with like local councils and you want to show them how the building is going to look in reality. They can go inside and you can guide them because it's a shared experience. And basically you can be looking both at the same model at the same time, and then you're pointing at different parts of it as well. And it's very important that you actually, because you're in the space, you can easily remove your headset and put your headset back in order to see kind of the differences of the new and added building that you're adding to the space. We can do this also in AR using just tablets, so you can easily move the tablet and see what's happening in your surrounding as well. Okay, jumping to another topic, which is basically a very oops, sorry, my PowerPoint keeps stopping, so we can start one more time. So actually the next topic that I'm going to discuss is machine learning, which is like all the rave currently as well. And we have multiple projects in the office that tries to see how we can implement this technology into kind of our design. Let's see if that works. Oh, here you go. In our process. So this is a project that we have done in collaboration with Autodesk, and it was looking at this kind of materials that can deform shape under heat. And the idea is what we can do is we can try to simulate this material. We get a lot of data from simulating it, and then we can build a machine learning model that can detect how this material is going to behave. And that's very important because it means we can actually design how we want the material to behave, for example, on a facade, and predict how we should manufacture this kind of laminate material. So those kind of ideas have might actually change how we build buildings that are actually interact with the environment surrounding them. We also use it to make our analysis faster. This analysis visual connectivity, and basically this analysis usually takes a long time. But what we can do is we can train a model and that can predict this analysis without having to run it, and we can go and actually run it in Rhino, for example. So you can see here we're defining where our walls are, and then you will see the analysis running from the machine learning model, for example, directly in Rhino. We've also built lots of interesting stuff like semantic search as well, which allow us to search for files, but using normal sentences rather than searching for the name of the file and so on. And other stuff that we're using was diffusion models that we're building as well in this office. We also try to do what we call the twins, digital twins of buildings, and digital twins are very important because basically can tell us how the building is performing and allow us to change some stuff to adapt to the users, or also be able to improve our designs later on because of how we think the buildings are working. And we actually have a model of our main office here in London. And as you can see, we have a lot of temperature detection and light detection and light sensor, temperature sensor, pollution sensors that can tell us at any given time how the building is performing and where the people are moving around our campus. But we can take this as well to the construction site. Instead of like building a twin for a building that's already built, can build what we call a construction twin. And in here, this was like a collaboration between us and Boston Dynamics early on in the process when they started producing this robot called Spot. And what we were doing is we're taking Spot on site, we're making it learn a path around the building, and basically Spot can go and do this task every week and do a 3D scan of the building. And this 3D scan basically will allow us to go in a timeline and check all the progression of the construction site while it's happening. Also make sure that the design is matching the work that's happening on the construction site is matching the design. And we can change all this as well if there is any problem, for example, like something is off or not the right place. We have been doing this during the pandemic, and we continue with our collaboration with Boston Dynamics as well on different projects till now. Thank you very much.
Thank you, Khaled. Thanks for the talk. That was an interesting one. Maybe with a couple of questions, we can start the Q&A.
Amazing work.
Session.
Sorry,
Yeah.
sorry, Mo. I have to say this is amazing work you're doing, guys. Really, very advanced, and it was really very, very, very informative.
And thank you. I mean, well, I'm lucky to be part of the group here at Foster, because we have been doing this for a long time as well, and the important part is kind of the applied part. So we try to take all the stuff and actually get them projects, which kind of like try to advance our design process bit by bit as well, which I think is an interesting part when you try to combine kind of research and practice together at the same time.
And I think Khaled, that's the toughest part, I believe. So maybe that's the first question: is to which extent do you think the designers are being integrated in all of your researches, or in other words, when do when your designers would step in the process of being? Do you actually filter what you come up with, or do they get to choose based on your options, or do you do recommendations to the designers?
So for the kind of the optimization, what we do is first we define a parametric model that we want to build. So we build, and this have like a little bit of art how we build a parametric model that can kind of cover all the options that you need to produce. First, we do that. We sit with the team, we build a parametric model to whatever their inspiration is in terms of design. Second thing is the criteria. So, for example, for an office, we might look at daylight. For example, for an airport, we might look at connectivity and so on to define 3 or 4 key criteria that we want to target. And the third part is like running it, give it to a computer, try to figure out what's the best. And the last part is we get the best options, the best 10 options, and these are the only ones we show to the designers. So we tell you guys, we have these 10 options. One of them is performing very well in views, one is performing, because there's always going to be a trade-off. There's nothing that's, most of the time, there's nothing that's performing well in everything. But what you can get is something that may perform very good in views and medium and daylight and so on. And there will, the designer comes and checks, actually, I might think this criteria is better for me. And they take this option and start building the more kind of architectural model on top of it. So it's all a conversation. Actually, in the office, we work as a consultancy. So we work, as you see, we work with many projects, and they come to us with like questions or problems, and we work with them in order to solve it for them. So that's why we can have, I will be having like 3-4 projects running at the same time, all like asking different questions.
Yeah, so once recommending options, let's say 10 options out of the machine to the designers, and then you think there should be also a touch of the designers to modify these options. Do you think that you have any of the projects where what came out of the machine was really applied up to 90%, and that project was built, or what's the percentage of what's taken from the machine being applied to the project? Because this is very important to understand the ratio of the input of a designer based on what's the outcome of the machine, or the percentage of the designer.
No, for the project I've seen, the end results are actually very close. So what happens is, for example, for the Guangming hub, from the optimizations, they now knew where they want to build all their massing in order to get like the best daylight, the connectivity, and so on. And then they will go and then work on top of it and start editing. And basically, we take their options that they produced, we analyze it using the same tools again, and we can keep comparing it to like the best options we have. So they start having these conversations going back and forth. But I would say, especially for Vanderbilt, the options that was produced was very, very close to what the guys had in terms of where the massing is. And then they start putting all the architecture bits on top of it afterwards.
That's interesting. So
and Khaled, sorry, the designer is actually inputting the parameter, correct? So the designer is, doing the parameter aspects or what the client is asking for, and then he or she would be inputting these parameters. So it's maybe a different type of designer rather than, the conventional, traditional one, correct?
Yeah, no, so that's why we sit with the team. Maybe we will be building the model, but it's all their inputs, and maybe it's some of the conversation on some of the models that we already created manually, and we start figuring out which kind of design aspects we can put in the model, because it's as you see with optimization, it's very easy for the optimization to find a loophole. And for example, it's you tell it like, I want daylight everywhere, it creates like this tiny, very tall tower, or like something. I want all these areas will build like a wall, stuff like this. So there is like a lot of art into constraining your model to produce options that the design team actually thinks are useful in terms of architecture. And this is like the whole balance we try to get to. That actually our parametric model produce options that are very similar to what they want, but can produce like thousands of them. And then we build all the analysis on top of it.
And also, Khaled, about bridging the gap, because that's maybe the R&D team is there to bridge the gap between research and academia and practice. So what's the biggest challenge in your opinion in this gap, or in bridging the gap?
It was for us actually trying to present because actually all of us are teaching or like doing PhDs and so on. So we live both into kind of sometimes the state-of-the-art academia bit and also office bit that's working here, and trying to present this stuff in a way that the designer will understand it and take advantage of it. It's always a problem. And again, something that we learned a lot, how we can build a presentation that's you can present in 5 minutes for a specific problem. Presentations that you can actually get all your information out and get the core problem rather than actually talk about technicalities, about how the system works, all that kind of stuff. So I would say this is the hardest bit. It's like you're trying to present our work for designers in a way that they will see valuable for them and understand it in like in a 10-minute presentation, for example.
Yeah, so maybe we go back to the optimization process. You talked about the parameters that are getting into the optimization process as functions that are required by either the designer or the client. But is there anything that used to, for example, any other maybe parameters that talks about the materials or the financial part, or the geometries that are being generated that are purely functional geometries that tackles the functions that are being inputted?
No, we have actually, we do this a lot, and sometimes in the optimization, but also in our kind of the design tools like Sandbox and Thalia. And these all like are tools that basically want to get as much metrics as possible. And a lot of it is comes to also financial stuff. So we have a project that will, for example, we're talking with a client about, each apartment that, for example, sees the water will have this percentage over over an apartment that doesn't. So we can take our view analysis, we can combine it with this information that we have, and we can give them like a value proposition of actually this option is more valuable than this option. And again, for the well-being, for example, stuff we've done. So it's actually, again, this option will perform better for the people that are in it because you have amenities around and you have all green areas surrounding you and so on, that we can give you a score for as well for each of these options. So we tried to do the right word for it, quantify kind of stuff that might not be unquantifiable in order to get like a number for a building that's performing. And again, sometimes it's financial, so just like a number in dollars. Sometimes it's more stuff like walkability and your comfort in space, stuff like this. But as much as possible, we try to get them into like a chart so you can actually see which options perform better than others.
I think that would be. Thank you very much, Khaled, for
Khaled, I have just one more question, if you don't mind, Mohannad.
No, for sure.
I'm specifically interested in one thing that you showed, which is, we had 2 people on the street putting the head-mounted display and looking at probably a digital version of something. So the question is, was it the plot there empty and they were looking at the design being scale 1:1, or was it something that was mapped on top of an existing building? What was the action happening there, and what actually type of software you used for that?
Okay, so for this one, it was actually for the tulip, which didn't go through, didn't get built in there. So basically, the site was empty next to the gherkin. You can basically walk, and then you can see it on site. So we had this conversation with the council in order to see actually how it might look like in place. And we used Unreal for this one, but we built a lot of tools on top in order to do the tracking outside successfully. So marker tracking, I mean, all stuff are they're around. They're not like new, but like packaging them into this package for the outdoor, like the hard part. So doing marker tracking and doing like inside-out tracking in the model, and all what you need to communicate between these 2 people in the model and so on. This was like the hard part, like bringing it all together.
Yes, but it was a virtual reality experience or an augmented reality experience using the head-mounted display?
For the head-mounted, it was virtual. And we had for the same project, we had the iPad as well. So you can do the iPad, which is just AR on site, or the virtual reality, which you just put in. It's completely virtual. And we work a lot with our visualization team, which produces like super high quality models for our options. And then when you put it in, I would say you have it's not like you have a good experience what the space surrounding you and the materiality and so on is as well.
Fantastic. Thank you so much, Khaled.
Thanks, Khaled, again for the talk. I think it was an interesting one. We have it recorded, so we get to AED community to view this online. I'm sure they will benefit from the talk. So thanks, Khaled, for being here, and thanks for the talk, and thanks, George. Thank you, everyone.
Thank you very much, and hope to see you guys soon.
See you. Bye bye.